This course is a graduate level introduction to condensed matter physics, and it will be assumed that everybody knows a little bit of condensed matter physics. Everybody's familiar with basic undergraduate concepts of condensed matter physics. So those of you who have never seen any solid state or condensed matter physics will have to work slightly harder for the first 2 or 3 days of this week. And the first 2 tutorials that you will now see are aimed at kind of leveling the field for everybody. So those 2 tutorials will go over this material that I expect everybody to know, which is the basic lore of crystalline lattices, Brillouin zones, degenerate Fermi gas, Fermi velocity, Fermi energy, and these sorts of things, which we will encounter as we go along. And we will, I will remind you what these are, but I will not be lecturing and explaining them in detail, because in 15 lectures that we have at our disposal here, I could spend half of that time kind of going through basic undergraduate solid-state physics, and that would be repetitive for those of you who already saw this course. Basically, this is the condensed matter Bible, which is the good old Ashcroft and Mermin. And what I'll be assuming is that you guys are familiar roughly with first 5 chapters of this book, which discusses these issues that I just mentioned. And what I ask you or invite you to do after this lecture, when you have time this afternoon, to go over these first 2 tutorials, read those problems, and decide for yourself. If the material there seems familiar, then you don't really have to do anything. You just come to the tutorial on Tuesday and Wednesday, and you solve these problems. If this seems just completely new and you never heard it, then I ask you to read these chapters from the book. And for a graduate student of your caliber, it will be absolutely no problem to catch up with this material, because it's really simple. Okay? I'm not sure what the situation with books is here. Probably the library will have a copy. If not, I'm happy to let you copy.
So, this book,
yes,
by Ashcroft and Mermin, this is the introductory book to solid-state physics. So we have approximately around 10 or 12 authors in David's office. So
excellent. OK. So everybody who needs one should have access to this book. And please just study as much of it as necessary for solving these problems in the tutorial, and then everybody will be fine. What I will focus on in this course is graduate level condensed matter physics, which assumes that you know some of these basics. OK, so let's start doing something useful. Condensed matter physics, sometimes people talk about solid-state physics. So let's start thinking about what is the same and what is different between these two. And in order to address that, let me first ask this question. So what is a solid? And it's a question to the audience. How would you define something that is solid? Yes? Lattice. OK. Do all solids necessarily have lattices? Does some piece of plastic have a lattice? No. They're amorphous solids. Actually, most of solids that you see around you don't have any lattices. Wood, much of what you see is made of wood. All sorts of plastics, glass, they don't have any regular structure. Yet we consider them solids. So what is a more general definition of a solid? Suggestions?
Something rigid?
Something rigid, yeah. We're coming closer. How would one define rigidity in kind of physical terms? What sort of, say, experiment you would do to prove that something is a solid?
Doesn't have translations. Doesn't have translation symmetry.
Does have translation?
Doesn't lack of translation symmetry.
Lack of translation symmetry. Well,
Of the constituents. Couldn't move, I mean, couldn't translate the constituents. And keep it
okay, there's another suggestion back there.
Try and shear it. Solid state
Ah.
shear.
Okay, that's the definition. So solid is a physical system that resists shear deformation. Okay, and let's try to contrast it with a liquid, right? If you take a liquid, it resists compression. You cannot compress liquid very much when it's in a closed vessel. And solid also you cannot compress. But the difference between solid and a liquid is that this chalk, I cannot really shear it. If this chalk was made out of liquid, I could easily bend it or shear. It would not resist shear deformation. So solid is a system that resists shear. In other words, more precisely, it's a system that has non-vanishing shear modulus. And liquids and gases have shear modulus that is exactly vanishing, whereas solids have a shear modulus that is non-vanishing. There is something intermediate, which is glasses. Glass, like a window glass, interestingly, on short time scales, also looks like a solid in that it resists shear. But on long time scales, actually, these things flow. So if you look in old cathedrals at windows, they're actually a little thicker at the bottom than at the top, just because, not that they were made that way, but in a long time, this glass actually flowed down a little bit. And in another few thousand years, maybe it's going to be totally thin on top and thicker at the bottom. Was there a question?
Are materials ever compressible but resistant to shear?
Say it again.
Are materials ever compressible but resistant to shear?
Materials that are compressible, are they resist to shear?
Do there exist materials that are compressible but resistant to shear? I was just wondering.
I don't
why
think
you
so.
Also include that. Okay.
I don't think so. Okay, so what's then? So solid-state physics obviously deals with things that are solids in this way, and solid-state physics has some enormous successes, especially when it comes to metals and semiconductors. All our computers, iPods are based on our understanding of solid-state physics. What's the relation then to condensed matter physics? Condensed matter is basically a more modern label on solid-state physics, and it includes lots of things that are not solids in the traditional sense of the word. For instance, condensed matter physics also studies certain types of liquids, like liquid helium, which is a kind of very interesting quantum system. And we will actually study some of these more general condensed matter systems in this class as well, superfluids, for instance. So solids and some liquids, according to this modern definition, are interacting quantum many-body systems. So condensed matter physics is concerned with interacting quantum many-body systems, and that's what makes this topic very difficult in some cases, and also very interesting. So let me start this lecture by writing what one may call a condensed matter theory of everything. And unlike some of the other disciplines that you study in this institute, condensed matter is a bit different because we kind of know all the fundamental laws of physics that govern solids. It's just basically quantum mechanics and statistical mechanics. And one can very easily write down the kind of theory of everything in condensed matter physics. And it's a relatively simple Hamiltonian that looks like this. I will first write and then explain. And when I say simple, I mean this simple in quotation marks because it will still take the whole blackboard to write down. But nevertheless, it's simple in a sense that we understand every single term and we understand it well. Okay, so this is the Hamiltonian. Hopefully, no more mistakes. So what you see here, a solid is composed of typically some lattice of nuclei that are positively charged, and they form a lattice. And what this first term is the kinetic energy of those nuclei. They have mass m and charge z times e. And then there's a bunch of electrons. Some of them are free electrons that can propagate in the entire solid. Some of them are bound to these nuclei. These are called core electrons. And their kinetic energy is here. Their mass is just lowercase m. And then the rest here is just a Coulomb interaction. They all are charged particles. So this is the Coulomb interaction. This first one we call, let me call it VII. So this is interaction, just Coulomb interaction between individual nuclei. This will be a term that is interaction between electrons. And this is the interaction between electrons and nuclei. Okay? These are the kinetic energies. Sometimes we call this Ti and T of electron. Okay? So it's a Hamiltonian that is kind of very simple conceptually. And so you may ask, what is there left to study? We write down the Hamiltonian, we can just solve it, and all the solids just come out from this theory, right? And you would be right. It's just that solving this is an extremely non-trivial issue. And the reason for that is that it's an interacting quantum many-body system. And I put emphasis on this many-body here because, you remember, what's the typical number of atoms in, say, a cubic centimeter of a solid? Anybody remembers? 10 to 23, 10 to 24, depends on the density. It's roughly the Avogadro's number, right? This is a huge number in every cubic centimeter of, say, copper metal or iron metal. It's that many atoms. So these indices run from 1 to this number, right? So now let's see, how could we solve this problem? Well, maybe you can say we can start with some small numbers. Let's, so this is number of atoms in a cubic centimeter of a solid. And obviously, this would not be a good idea to start solving for this large number. So let's start with small numbers, right? So let's take n equals 1. So what is this for n equals 1?
1 electron and 1 hydrogen or something?
Yeah, hydrogen atom. And this we can solve exactly, right? You open your favorite quantum mechanics book, and on page 76, there will be full solution with the radial functions and everything. We know the spectrum. So this is good, hydrogen. We can solve it quantum mechanically. So that's a good start. Now, let's take n equals 2. So what is this? That's helium, right? Now, helium, you open that same quantum mechanics book, and you will find that there's no exact solution for a helium atom, because already that's a non-trivial interacting problem, and there's good approximations, but the exact solution doesn't exist. And then you go down, and between 2 and, say, 100, and that's your periodic table. So this is your atomic physics. And there's thick books on atomic physics, and it is fair to say that atoms are pretty well understood based on this, say, 100 years of development. Well, maybe not quite 100, but maybe 70 years of development of atomic physics. We understand individual atoms pretty well, but we're still, n is 10 to 2, not 10 to 23. Then you ratchet up the game, and you take n to range between, say, 100 and, I don't know, maybe 10 to 5. What is that? Well, that's molecules, right? So if you take a DNA could have millions of base pairs. So this is molecules potentially large. And yeah, it's true. This is studied in chemistry. And now, you see, when you study things like DNA, it's really, people rarely start from this Hamiltonian, right? It's chemistry. They study the constituent base pairs, and they study interactions between them. They write down effective Hamiltonians. They do numerical simulations. So even for relatively small numbers of n compared to 10 to 23, you're already using completely different methods than for the hydrogen atom, right? So this gives you an idea why when n is very large, macroscopically large, 10 to 23, then the system just becomes not just quantitatively different, but qualitatively different. And indeed, solids are different than individual atoms, and that's what the solid-state physics or condensed matter physics is all about. Any questions about any of this so far? So let me I'm just trying to impress you now a little bit. Pauli.
Yeah, just a question.
Question. Was there a question?
So you call this a theory of everything, but
yes.
But even for the n equals 1 case, this model doesn't capture everything. It doesn't capture fine, hyperfine structure, for instance.
Yes.
So it's
yes.
clearly not relativistic. So
yes, I agree. So it's a theory of everything which lacks the in condensed matter context. What it lacks is spin, right? Spin is a kind of relativistic effect, and we know how to handle spin. I just want to not to complicate this any further, right? And that's absolutely right. We will add to this relativistic corrections, and this mainly comes in the form of spin-orbit interactions, magnetism. But at this point, yeah, the point is we very well understand those effects as well. I just didn't want to clutter the blackboard, but that's a very good point. OK, so the problem, so you can say, OK, so if we cannot really solve these problems analytically, can't we just put this on a computer and take a given solid and try to solve this Hamiltonian by some numerical method. Okay? And even that proves to be very difficult. Let me just try to estimate the size of the Hilbert space for this quantum mechanical problem. And it's going to be a very, very crude estimate. Yeah, the problem with this is that those variables are all continuous, right? Momenta and position. So in order to estimate the size of the Hilbert space, one would have to do some fancy division of space to small segments and so on. But I don't want to go through that. But let's just say one has 10 to 23 particles, and each is a spin 1/2. Okay? And we completely disregard all the motional degrees of freedom, just consider their spin. So each particle can be either up or down. Okay? 2 states per particle. Which for electrons, it's certainly true. And you can believe me that the Hilbert space of that Hamiltonian has many more states than just this. So this is a kind of simplest lower bound, right? So in this case, the total number of states in the Hilbert space when there's 2 states per particle will be 2 to n, which is 2 to 10 to 23. And this is, well, this is a huge number, right? This is roughly, say, 10 to 10 to, well, it's still 23 up to logarithmic corrections, right? Now, imagine you want to encode this Hilbert space in some classical computer, right? This makes you think, right? So imagine you had a really efficient computer such that you can encode 1 bit in an atom, right? Probably you cannot go any smaller. So how many atoms are there in the text? Any guesses? You can find this in Wikipedia, or you can do a simple estimate. And roughly, it's 3.8 times 10 to 50 atoms comprising the Earth. Right? Now, compare these 2 numbers. I mean, this number is like 0 compared to nothing. Let's get a computer of the size of the whole Earth. And each atom would encode 1 bit. You would not even come close to encoding the Hilbert space needed for 10 to 23 particles. And I'm only counting their spin. I completely disregarded their motional degrees of freedom. So let's go a little bigger. The sun, right? The number of atoms in the sun is impressively bigger than the Earth, but still on this scale, it's really times 10 to 57. Right? That doesn't really make a difference. Right? This is 10 to 10 with 23 zeros right here. This is nothing. So let's go to the whole universe. We have a computer where the whole visible universe is forming our qubits, and this is 1.3. This is an estimate, of course, times 10 to 79. So this is a much larger number than these 2, but still is ridiculously small compared to the number of bits that we would need to encode this Hilbert space. And so that should give you an idea why it's completely hopeless to try solving this problem with this many particles by brute force. You just cannot do that. And that's why condensed matter physics is so interesting, that we have to develop these new methods to account for this large number of particles. And let me also remind you that things like living things, like us, they're also described by this Hamiltonian, right? Somewhat more particles than our brain is described by that. So all sorts of interesting things happen as you increase complexity. Okay, so what I'm going to do today, in the remaining less than an hour now, I'm gonna start chipping away at this condensed matter theory of everything. And we do this in steps. We kind of divide and conquer. We develop approximations for this enormous Hamiltonian, which allow us to slowly focus on certain parts of it and treat it systematically and start kind of wrestling out of this very complicated Hamiltonian some properties that resemble those of solids that are around us. Okay? And as we go along, we will see how this works, and we will see where it works, where it fails, and then based on the failures of these approaches, we will then try to develop new ones, and hopefully by the end of this course we reach, if not quite the boundary of the unknown, we reach to modern times in this field. Okay, so what I'm going to start with is the so-called Born-Oppenheimer approximation. This was developed a long time ago, in the early days of quantum mechanics, back in the 30s, where people started pondering precisely this Hamiltonian. And Born-Oppenheimer approximation, basically what it does, it recognizes that these ions, M, have a much larger mass than electrons, and therefore one can solve this problem in a manner that basically solves for electrons while these ions are treated quasi-statically. Okay? So this is basically an expansion in a small parameter. Which is electron mass divided by ion mass, and anybody tell me what this typically would be? Say in a hydrogen metal. So in various solids, this would range between 10 to minus 3 all the way to 10 to minus 5. So in hydrogen atom, it would be roughly 1 over 1,000. In some heavy metal like lead, it would be larger. And in this approximation, like I said, it is possible to separate the motion of ions from the motion of electrons, and that is a very useful simplification of this big problem. It will turn out that the expansion parameter somewhat disappointingly is the real expansion parameter is actually m over m to the power 1/4, which is only of the order of 1/10, but this turns out to be good enough for most purposes. Okay, so these considerations usually start with first step, which is a simplification of this Hamiltonian that recognizes that not all electrons are equal in a solid. A large number of electrons are typically tightly bound to the individual nuclei, and therefore, for the most purposes, we can basically treat them as being a part of this quasi-static ion. Okay, so we combine those electrons and with the nuclei and think about ions, and then we have some electrons that are freely moving in a solid, and those have to be treated separately. So we separate, this is the first step. And the Hamiltonian that results from this has a very similar form to that one. 1 over I, di squared over 2n plus So the Hamiltonian now looks like this. I have simply separated once again all the electrons into those that are bound, tightly bound to the nuclei, and they now basically increase this mass of the ion a little bit, but not by much because they are much lighter. Well, they also, so here in the kinetic energy, I'm only explicitly summing over those free electrons that are not bound to the individual nuclei. But what also happened is that the interaction between the individual ions is now not just the straight Coulomb as it was between the individual nuclei, but is now slightly modified because, of course, these electrons can no longer be truly considered point-like, right? They have some wave functions that extend over a length scale that is comparable to the intra-ionic distance, and therefore the Coulomb potential is somewhat modified, and that's recognized by me writing some ionic potential here. Electrons still interact via straight Coulomb, but electrons with ions, again, interact with some potential that has been slightly screened by these core electrons. So let me just write that. And just to make it more concrete, let me give you an example here. So for instance,
the J in your last term, is that the J in free electrons?
yes, so this J would also be relevant to free electrons. Any other questions? Okay, so one example that I can give, a very simple example, is a sodium metal. One of the simplest metals that you can have, just a lattice of sodium atoms. And sodium is very simple because it has atomic number Z equals 11, and the atomic structure of sodium looks like this: 1s2, 2s2, 2p6, 3s. So what this means? This means that in the lowest orbital there is 2s electrons. In the second orbital there is 2s electrons and 6p electrons. And then in the third orbital there is 1s electron. And the important thing to recognize is that this atomic configuration is the same as neon. Neon has Z equals 10, and this is a filled shell, right? Neon is an inert gas, So basically, a lattice of sodium atoms you can think of as individual ions being neon inert atoms. Of course, they have charge 1 because they are missing one electron, because nucleus is that of a sodium, Z equals 11. And then each of these atoms contribute one conduction electron or free electron that is roaming around these, the whole lattice. Okay? And so what we would do in this case, we would take all these 10 electrons and subsume them to this core, and we would get this bunch of nuclei, bunch of ions with charge 1, and the free electrons would just be this one s electron that has been so-called donated into the conduction bank of the metal. Now, this already is a huge simplification compared to this case, because where previously we had 11 electrons per atom that were independent, here now we have just one. Okay? In this extreme case, it's a tenfold simplification of the problem, but the problem remains hugely complicated still. But this is almost for free. But we have the simplification, so we take it, and from now on we consider this Hamiltonian, which describes a system of ions and free or conduction electrons. Any questions? Okay, so now I'm going to explain the Born-Oppenheimer approximation proper. And once again, that will rely on exploiting this small parameter, mass of electron divided by the mass of the ion, which is 10 to minus 3 to 10 to minus 5. And basically, as you may intuitively imagine, when you have a bunch of these heavy ions, they move relatively slowly compared to these electrons, which will be moving fast because they are light. And therefore, one expects intuitively that one can solve the problem of electrons with these ions basically being held in the fixed positions. And this Born-Oppenheimer approximation actually provides a framework for this. So what we want to do, we want to solve the problem with this Hamiltonian. This is just a Schrödinger equation. And when I write this capital R, little r, that's an abbreviation for the full, I mean, of course, what I mean here, this R is a stand-in for all Ri, and this little r is a stand-in for all the electron coordinates, but of course I don't want to write 10 to 23 coordinates here, so I will write this Schrödinger equation in this simple form, but remember that what this means actually is 10 to 23 vector variables hide in there. So the way we proceed is as follows. We write this wave function in the following form. where this thing here, this psi with subscript e and index n, is an electron wave function for all ionic coordinates being held fixed. So this in other words, this psi with subscript e is an eigenstate of the following Hamiltonian. Where TE, DEE, and VEI are these guys here. So if I hold the electron, the ion coordinates fixed, then and then just solve for electronic wave function, then I just have to take into account this term, and that term. Okay? Because if ions are being held fixed, then they have no momenta. And this is just a constant term. So I'm just solving that. And then, of course, these psi n are solutions of a Schrödinger equation, and therefore they form a complete set. So what I can say, what this means, is that I can expand the full solution of the problem in terms of this basis set, and these phi n's are coefficients of expansion. Sometimes we call them ionic wave functions. But technically, they are just coefficients of expansion. And what we still need to find is what are these coefficients for. It's a formal decomposition of a full solution of a complicated equation in eigenstate of this electron-only problem. And now we have to determine what these coefficients are, and how do we do that?
So, a question about the spring potential, like analytically, what do we expect it to look like, the spring cooling potential? What sort of expression do we expect for it?
So basically, yeah, this is again a topic discussed in atomic physics at length. What happens is that you have truly point-like positive charge, which is your nucleus,
Sure.
and then you have some charge, negative charge, distributed in some distribution, let's call it rho of r, which presumably decays on some length scale given by Bohr radius, right? So this spin Coulomb interaction is basically given by electrostatics of this charge distribution, and once you know what are the wave functions, in this case of neon, you can calculate it to arbitrary approximation. Any other questions? Okay, so how do we determine these coefficients in the expansion? How do we always do this? there's only one way of doing that, right?
Fourier transform.
Can you speak up?
I'm doing a Fourier transform and expanding it in the Fourier basis.
Any other suggestions? Well, we plug it back into the original Schrödinger equation, right? So that's the general method in quantum mechanics. We have a general extension. We plug this back into the Schrödinger equation and see what are the equations for these psi's, which sometimes Fourier transform might be useful for this, but more generally, this is what we do. Okay, so the next step in this construction is take psi RR and substitute to the Schrödinger equation. And we know what happens, right? So this Hamiltonian H we can write as in symbolic form as Ti plus the electron plus Vii plus B electron plus C electron ion, and the Schrödinger equation can be then written like this. What I did here, I took this extension, right, and I hit it with this Hamiltonian here, okay? And I recognized that this part, the electron kinetic energy, the electron potential energy, and the electron ion potential energy, I can just commute through this phi of n, okay? Because it does not contain any operators that would act non-trivially on this phi of n. And so I act with this simply on the electron part of the wave function. Okay? These other pieces here, the ion kinetic energy and the ion potential energy, I cannot do that because, for instance, this guy here has a derivative hidden in this momentum operator here that acts on this coefficient r. So it acts non-trivially both on this coefficient and the electron wave function. Right? So I just leave it out. But here, this part, I can actually look up here, and I see that I have chosen my electron wave function exactly in such a way that this operator acting on it just gives me the energy eigenvalue right there. And so this results in a simplification, but I still have to deal with this first piece. Okay? So let me organize my whiteboard here. And let me proceed to the next step. So let me now look at this term here. And again, you can see that the second term is kind of easy to handle because the potential doesn't have any non-trivial operators such as derivatives. It's just basically a scalar function, and there's nothing really I can do with that. But this guy here, the kinetic energy term, has momentum in it, which has a derivative operator, which will act on the product, and I have to figure out how this works. Okay? So what I'm looking at is this term, I acting on psi, and so what I want to do ultimately, and I forgot that step. So as the next step that I will do, I will multiply this equation from the left by psi Cm star R, capital R, and then I will integrate over d3r. Right? This is how I get rid of these electron wave functions. And remember, our goal is now to find an equation for this psi. So that's what you always do, that you make use of orthogonality of your wave functions, and that's the next step. Okay, so now imagine I just focus on this term with ti. I hit it with the left with this wave function and integrate it d3r. So let me just write what is left. I have sum over n, which is just sum from the extension. I have this integral d3r. I copy psi e and r, capital R, and now I have to write this. Looking at psi and capital R, psi R, capital R, and this term here, I have to recognize that this guy, which is minus h bar squared Laplace with respect to Ri squared divided by m when I write my momentum operator. Yes?
You've got psi em. Do you need another phi in that situation?
No, because remember, I just take this equation. It has both phi and psi. And like I said, I multiply it from the left by this and integrate over r. I just want to, I'm deriving an equation for this phi, and I want to get rid of all these psi's so that I have an independent equation for this phi. And the problem is that they're kind of entangled here through this operator acting both on one and the other. Okay? So this is the only complication that I have to handle. And well, it's not such a big complication. We know how to take derivatives, right? So we just use a product rule. So let me extend this here. And there will be three terms because this is a second derivative. So there will be one term when everything acts on the first term, one term when everything acts on the second term, but there will also be a term where one gradient acts here and another acts there. So I have to write out those three terms, and I get the following: minus h bar squared over 2m, sum of I, and I also have sum over n, and well, dr. Okay, so this is what I already said in words. There's three terms. One, when the Laplace acts on this first term, then I have a gradient acting on this, and the gradient acting on that, and then finally I have just this term, and Laplace is acting on the electron wave function as well.
In the last question, the gradient acts on small r.
No, so this gradient should be capital R.
Capital R, okay.
Yeah, it's a momentum like this, so it's a momentum of ionic coordinates, so this is actually. So notice that of all these terms, the one that is easy to calculate is the first one, because here the gradient, or this differential operator, only acts on this ionic wave function, and the integral that I have to perform here is over the electronic coordinate, and in the case of this first term, that integral is trivial. Basically, I just have an integral of a product of psi star psi, and that I can just get simply by orthogonality. So that integral is easy to evaluate. Unfortunately, that's the term that is most important, as we will show in a moment. So this is the most important term. And we will show that these two terms are small. They will be small by powers of this ratio. Okay? So for a moment, you just take my word for it that this term is dominant, and we can immediately evaluate it once again, because this integral just involves psi star times psi. Nothing else depends on lowercase r in there, and that those wave functions are by definition orthogonal. So if we neglect temporarily these two terms, then we can actually write down the resulting equation, and then we will show that these terms are small in a subsequent development. So, putting everything together, what we get is the following ionic equation. To leading order has this form. Sum over n I plus bii plus Cn r acting on phi of r is equal to sum over n over r. So that's basically just this equation. So here, you see, so I'm just rewriting this equation after I multiplied it by psi star and integrated over d3r. Here, in this term, I can get rid of psi en immediately because it just multiplied by this energy eigenvalue, and it gives me this right-hand side. Okay. All that's left is just this. Sorry, it just gives me this term here. All that's left is just the energy eigenvalue and psi of n, because these electron wave functions, they will drop out by orthogonality. From this first term, this guy, again, the electron wave function just drop out by orthogonality, and this Ti term, I just dealt with it here. I just kept this first term, and it gives me this. Now, if you look at the form of this equation, it's basically just the usual thing. In order for this sum to be valid, I have to require that the equation itself is valid without the sum. And I put a box around it, and the other equation that complements this is the equation up there, the electronic equation. So let me write it here once again. Okay, so let me now summarize. Yes, question.
Is this what's usually or sometimes called the adiabatic approximation?
Yes. Sometimes in the literature, this is called also adiabatic approximation.
So how did you get that order? Order of small m over capital M to the 1 over 4?
That's still something that we will discuss. Okay, in the last 20 minutes of this lecture, we will discuss that. But let me now summarize. Yes.
Is it the only approximation you've taken is dropping those two terms?
Yes. There's been no other approximation at this point.
In that equation, in the first box equation, what happened to phi n of r on the right hand side?
That disappeared, but should. Thank you. I had R, but I didn't. Okay. That's it. Okay. Now it's. Okay. So let me just summarize in case somebody lost the thread of thought in this development. So we start from this Hamiltonian, which describes ions and electrons, and we're solving the Schrödinger equation up there, h psi equals e psi, and we solve it in a way that we often solve Schrödinger equations. We find the basis, which is basis of states psi en of r, which are a solution of this electron-only problem with ions being frozen at specific ionic positions that are held constant. And then by substituting this back to the Schrödinger equation and doing some manipulation, we find that the coefficients, which we sometimes call ionic wave functions, are obtained by a Schrödinger-like equation into which this eigenvalue of the electronic part enters as a parameter. Right? So basically this offers a practical way of solving this enormously complicated problem in terms of two somewhat less complicated but still very complicated problems where the electron motion and ionic motion have been effectively separated. Right? So we don't have to solve them at the same time. We can solve them separately. Right? We only have to solve the electronic problem with ions being held fixed, and then we feed the result of that calculation into a problem of ions, and we can solve that separately. Now, of course, that relies on an approximation that somebody pointed out where we neglected those two terms, so we still need to show that this is a legitimate approximation. Okay, and this is what I'm going to do in the last 2 minutes of this lecture. discuss the smallest of the neglected terms. And for this, I have to adopt some sort of approximate form of these various wave functions. Because what I want to do, I want to estimate these gradients here, right? And in order to estimate them, I need to know, roughly speaking, how these wave functions behave. So for the ionic wave function, I have some lattice, and I will make an assumption, and this is a good assumption in cases like these, that these ions are held in place by some effective potential that can be expanded near its bottom to a second order, and there is some minimum which is roughly harmonic. And one can always do that near a minimum. Any function near a minimum can be expanded to second order. So this is basically a harmonic oscillator. So the wave function psi will be some ground state wave function of this harmonic oscillator, which I will write like this. Where I introduce some parameter b, which is just the typical width of this wave function, and just recalling the physics of harmonic oscillator.
Before you said that like R is a placeholder for each individual ion.
Yes.
So should this maybe be like Ri minus R?
Okay. So yes. Okay. So let's yeah. Okay, that's a good point. So let's write it like this. Ri, and let me write this one as this, where R naught is the equilibrium position of the ion, and Ri is its actual position. And this V squared is h bar over m omega, and this comes from the law of harmonic oscillators. So basically, I'm assuming that this potential is the usual 1/2 m omega squared, and in that case, the ground state wave function will have this form. And similarly, I will take the ionic, the electronic wave function psi, and it will be roughly e to the I kf plus r, where kf is the Fermi momentum, and its length is roughly 1 over a, where a is the lattice space. And if this looks puzzling to you, this is one of those instances of basic undergraduate solid-state physics where Fermi momentum is something that I will assume that everybody knows, and if you don't know this, then the first 3 chapters of Ashcroft and Mermin explain that, and it will be discussed next tutorial. Okay, so now I'm going to estimate the size of these 3 terms in turn. And let me take the first one of those. So this is the term that I actually keep. H bar squared over 2m Laplace squared Ri acting on phi n side n. And so I'm taking two derivatives of this wave function, right? So what will happen, I will get this factor down twice, and we'll just write that out. Okay, so this first thing here is, again, I'm getting this factor squared twice, and this factor from harmonic oscillator is just h over an omega, so I have an inverse of that. Delta, on the other hand, is a typical displacement in this type of a situation, which is what I get when, since I'm taking a derivative of this r squared, I'm getting something with the dimension of length here. So I take a typical displacement. And then what I do, I just take all this and massage it by into this form by acknowledging that this combination of constants is just the Fermi energy of the metal. One can also write this as h bar squared kf squared over 2m like this. That's just the Fermi energy. And also that this typical displacement will be a fraction of interlattice distance that goes like that. And again, one can obtain this just from harmonic oscillator physics. This is a kind of nice form because it has a dimensionless factor. It needs to have dimensions of energy. This is all energy times the two wave functions. Okay? So now let me look at the second term. The second term looks like this. Again, I just copy the free factor. I have a gradient of Ri phi m dotted into the same gradient. And again, I estimate this in a similar fashion. H bar over 2m. I'm just copying. Now here I just have a first derivative of my harmonic oscillator wave function, so I will have 1 power of this factor, m omega over h bar times delta. And then the second term, I'm taking a derivative of this wave function here, so I will basically get a kf here. And I have my wave function as before. And I again massage this to get it into this convenient form. And in this case, I'm getting, again, this ratio, but now to power 3/4. And again, I'm getting the Fermi energy out, phi n psi dn. And finally, I'm looking at the last term here. So here I have just a second derivative This is log log. And I can estimate it in a similar fashion. So here I get no powers of this because I don't have any derivatives of my phi, and I have 2 powers of kf. And again, I use these relations to estimate, to rewrite it in this more transparent fashion. And I'm left with m over n to the first power, and phi n phi. Yes.
So how does the typical displacement know about small m?
Okay.
Property of ion.
The typical displacement knows about small m because if you ask yourself, how does the lattice hold together? If you just put individual ions, positively charged ions, they would not be stable. They would just fly apart because they would repel each other. So this potential here is dependent on having all these free electrons around. And so, there's maybe another step that I could do to actually derive that if the time, we have time to do that. But it's the recognition of the fact that the stability of this ionic lattice depends on these free electrons being there. Because if they were not there, the lattice would not be stable. So that's a very good question.
And so phi n is the same for all n. So because it seems that we are taking the same wave function for every.
Okay, so we're just making a crude estimate in the ground state of this. So we're just taking a ground state wave function of this individual ion. Any other questions? So basically, let's just take a look at this. It's a crude estimate, but if nothing else, on dimensional grounds, it's correct. The first term we took, and this is the largest term because it has the smallest power of this. I'm sorry, this should be one. It has the smallest power of this small ratio, and then the subsequent terms that we neglected have larger powers of this small number, and this is an extra m divided by capital M to the power 1/4, and this has 1 more power of that. So we conclude that these 2 terms are small compared to the term that we kept, which I call 1 here, by n to 1/4 and m divided by m to 1/2. And as we said, this is roughly 1/10 in a typical solid. So the first term we can neglect at the roughly 10% level. The second term we can neglect at roughly 1% level. Typically, what you do in condensed matter physics, and we will follow this recipe as we go, we first start discussing motion of electrons in a frozen lattice. And in fact, in the very first approximation, we consider the positive charge of the ions just smeared around uniformly, the so-called Gilliu model, and then we start discussing what happens when you have actual periodic potential. Lots of interesting physics, specifically all the physics of metals and semiconductors come from that sort of treatment. And only then we start discussing what happens when these ions start to have some dynamics of their own, and that leads to theory of lattice vibrations, phonons, and so on. And finally, at some point, we start taking into account the second term that we neglected, which leads to electron-phonon interaction. And this actually gives rise to some very interesting phenomena, such as, for instance, superconductivity. It turns out that in almost all known superconductors, what happens is that this electron-phonon interaction produces effective attractive interaction between electrons, which in some cases can beat their Coulomb repulsion, and that then leads to this spectacular phenomenon of electrical flow without any resistance, or superconductivity. So those terms that we neglect sometimes can lead to something important. This last term, I don't think it leads to anything important that I know of, but the second term does. Are there any questions?
So this is an approximation to leading order in a small parameter. Is there any way to go beyond the leading order? Like in the perturbation theory, generally we'd like to go beyond leading order, and usually here you're saying that we neglect these things because we're in leading order there. But apart from having these, is there anything else that we get? I mean, apart from having these extra terms, is there anything else we get?
Well, yeah. So let me just emphasize that at this point, this is all exact, right? So there's these three terms, and there's nothing else, right? So in that sense, it's not an expansion where we are neglecting an infinite number of terms. It's basically an expansion where we neglect, in the lowest order approximation, 2 terms compared to the first one, and then when we go beyond the leading approximation, we include the second one, and we're just neglecting 1 term, right? So at this level, everything is exact. Right? Although the problem is then very difficult to solve when you keep all 3 terms. It's relatively simple to solve when you keep just 1. It's more complicated with 2. Any other questions? Okay, in that case, I think that's it for today, and I'll see you tomorrow.